This is the basis set. This is the basis, the fundamentals out of which all other charge distributions are created from. The basis for any charge distribution is staring at you right here. You've got dipoles, you've got constant potentials, you've got constant field. Can you give me a visual, an intuitive explanation for why the volume charge density inside is zero? And the answer to that question is yes, I can, and yes, we will. Folks, welcome to the next episode of Electromagnetism. Today, I'm excited to introduce you to the spherical Laplacian. This is a sphere. Let's check out the spherical Laplacian.
You said it's a slow ride, everything's gonna be alright. All I gotta do is just hold tight, everything is gonna be fine.
The goal of electrostatics is to find the electric fields associated with a charge distribution. Now we know that the best way to start with that is find the electric potential, which is a scalar, so it doesn't go in three different directions like the electric field. And the electric potential is easier to work with because you don't have to deal with vectors, right? Just like the first reason. So we've found a bunch of ways we can find electric potential, but one of them is very strong, especially when you don't know your volume charge density. In that case, we can use Poisson's equation, but modified for no volume charge, right? So if you're considering a space that has no volume charge or no charge at all, then Poisson's equation becomes Laplace's equation. And we've learned how to solve this for rectangular coordinates. The big idea is quite simple. You assume that the electric potential is a function of both x and y. And after doing that, you plug it in over here and you end up with a function with a differential equation like this. And after you take this differential equation and plop out the solutions, you find out that the solutions for x and y can either be non-oscillating, as in exponential, or oscillating, as in a sinusoidal. A linear combination of sines and cosines. And after you enforce your boundary conditions, you can decide, okay, maybe x is going to be exponential and y will be sinusoidal, or the other way around. And then finally, you would write your total electric potential function. You would write x of x, y of y, and if needed, z of z. If there's only two variables, x and y, then you'd only have one variable under the sub of c, and you'd have m going from 1 to infinity, right? So, and then your final step would be to figure out what is this expansion coefficient. And so to do so, you would leverage Fourier's trick, dx, employ Fourier's trick. This integral multiplied with sine with m instead of m prime would give you a over 2, for instance, and that would allow you to figure out the expansion coefficient. So the expansion coefficient along with your electric potential function is your answer. So that is how you solve the rectangular Laplacian. But today I'm going to show you how to solve the spherical Laplacian. How do you solve the Laplacian in spherical coordinates? Turns out the idea is the same, but it leads to quite different results. And so let's get started with our first problem. Folks, welcome to our first problem. Here's what we have. A solid spherical conductor of radius capital R carries the net charge capital Q. For part A, give the volume charge density rho for radius between 0 and capital R and surface charge density sigma at R equals capital R. Okay, so how are we going to give the volume charge density? I mean, we don't know anything about this sphere, do we? But there is one detail we must be careful not to omit. It is a conductor, right? It is a spherical conductor. And what do we know about conductors? What is the most important thing about conductors? Why do you go inside a conductor when there's a lightning storm? Because a conductor has no electric field inside. Well, but how does that help us find the charge density? Well, remember that the divergence of the electric field is rho over epsilon naught. Hence, if the electric field is 0, so must therefore be the volume charge density, right? In other words, inside a conductor, all the charges are free to move. So they repel each other. They go as far away as they possibly can from one another, right? And so they separate all the way out until they end up at the surface, until they can separate physically no more, until it is literally the surface itself that bounds them from separating any further. So, what is the answer to part 1? What is the volume charge density inside this charged sphere? Well, it's almost like a charged spherical shell, because there is no volume charge density, because there are no charges inside the spherical shell, because it's a conductor, right? In a conductor, there can be no charges inside. But if you're like me, you're sitting there wondering, no, I can't accept this. That's not enough. Give me more explanations, showing me why the electric field inside a conductor is 0. Can you give me a visual, an intuitive explanation for why the volume charge density inside is 0? And the answer to that question is, yes, I can, and yes, we will. So here's what we have. I'm going to show you an intuitive, dynamical explanation of why a conductor has 0 charge density inside, why everything has to separate. So consider a negatively charged wall right here and a spherical conductor. Now I'm going to take this and repeat it a few times so that I can show you step by step what happens to the conductor and the charged wall over time. So we have our negatively charged rod repeated 3 times. What is happening at the beginning? At the very beginning, we have an electric field solely due to this negatively charged rod. This electric field is coming in towards the rod, right? So it's coming in towards the rod because it's a negatively charged rod, right? All the electric field lines are going to be coming inwards, something like this. But of course, we're dealing with a conductor. And in a conductor, charges are free to move, right? So let's take a look at a pair of charges inside this conductor. What forces will they experience? First, we examine a positive charge. A positive charge will be attracted to this negative rod, whereas the negative charge shall be repelled. Okay, well, so what? So these two charges separate from one another and they end up at different sides of the sphere. Okay, well, so that's just one pair. So what? It doesn't make a big difference. There's still a bunch of charges in the conductor. So this, I say. In the very beginning, the net electric field is just the electric field due to the rod. But now, let's call this E sub rod, the electric field due to the rod. But now, that electric field is a little weakened. It's a little subdued, if you will. Because now there is an opposing electric field going from this positive to negative charge that weakens this initial electric field by just a tad bit. And so now the net electric field, which used to just be the electric field due to the rod, is lessened by the opposing electric field due to this positive and negative charge, which I'll just call the electric field. And so the net electric field is now still in the left-hand direction, but now it's a little weaker. And so I will demonstrate the net electric field with this green vector. That's the net electric field. This right here is the net electric field. Okay, so that is good. Now let's take a look at the third scenario. What happens after that? Well, now let's take a look at another pair of charges. Since the net electric field is in this left-hand direction, there's still going to be a net force, right? A net force acting on these two guys. What is that net force? Let's think about it. That net force, well, the positive charge is still going to be attracted to the direction of the net electric field. That's going to be the force on the positive charge. So positive charge will feel a force going this way. Negative charge will feel a force going this way, because positive charge, of course, will go in the direction of the electric field. Negative charge will go in the direction opposing the the electric field. So you're going to have a positive charge ending up here and negative charge ending up here, right? And so in the third scenario, what we have is another pair of charges have separated. And so the electric field has weakened just a tad bit more. What used to be an electric field that was unopposed, simply going to the left, as it were, is now challenged by these two pair of charges that have already separated, and more are going to separate it. What used to be an unaltered electric field going just due to the rod to the left has now been challenged by two challengers. And now this original electric field due to the rod is much more subdued. This is the net electric field. And so as long as the net electric field is still in the left-hand direction, more charges will separate, right? Because more positive charges will get attracted to the negative rod, and more negative charges will get repelled until the net electric field is zero inside the conductor. Until the net electric field is zero, charges will keep separating. And so it so happens that until the electric field inside the conductor is reduced not to 0.5, but to 0, nil, all the charges will separate. That is the big idea. That is the reason why the electric field is zero inside conductors. Because until the electric field is zero, these guys will keep feeling a force, a need to separate. And until that force is zero, until that field is zero, which will create the force being zero, only then will they stop separating. And by then the electric field inside will be zero. So that is why the volume charge density is zero inside a conductor. Now, for a long time, I was very uncomfortable with this. Why does it have to be zero? It seems so uncanny. But I accepted it for too long. But then I stumbled on this magical explanation, and I hope it has helped you accept this fact as well as I have accepted it. Now, we consider the charge density, sigma, the surface charge density, sigma, at the edge of the sphere. What is that surface charge density going to be? Well, let's examine it. Since we know the volume charge density is zero, we know all the charges must now reside at the surface. Okay, well, now that's pretty easy. We know that the surface charge density sigma is described by what? Well, sigma is no more than the total charge divided by the surface area of our sphere. Because remember, surface charge density is simply how much charges you have on that surface divided by how big is that surface, right? Area. And that's all there is to part A. Now let's take a look at part B. Find the electric fields inside and outside the sphere. Well, inside, we know what the electric field is because we saw that the volume charge density was nil, zero, right? So since the volume charge density was zero, the electric field must therefore also be zero. Why is that? Well, since rho is zero, and remember that Gauss's law tells us the divergence of the electric field is nothing more than the volume charge density over epsilon naught. If the volume charge density is zero, then what do we get? The divergence of E is zero. Okay, well, there you go. So the electric field is no more than zero. Okay, now let's take a look at the electric field outside of the sphere. Let me just make it a vector right there. The electric field outside the sphere is simply going to be due to this surface charge density. The electric field outside the sphere, in fact, will look like a point charge, right? So E outside the sphere, R greater than R, is simply going to be K, which in SI units is 1 over 4 pi epsilon naught, Q over R squared. There you go. And if you think that there's a reason why this and this look awfully similar, well, it's because it is, right? This comes straight, this is almost like the divergence of the electric fields, and from there you can arrive at this. So we have answered parts 1 and 2. Let's take a look at the electric potential inside and outside the sphere. Well, we are told that the electric potential ground is at infinity, spatial infinity, as it often is. So at infinity, our electric potential is apparently 0. That is our ground. And we have to find the electric potential inside the sphere and outside the sphere. Well, that is not too bad. Let's do it. Okay, so the electric potential outside the sphere is going to be easier to find first because it's right where the ground is, right? If we try to find the electric potential inside here, well, first we have to know what the potential outside is so we can set it to the boundary. Okay, so let's try to find the potential outside first. So first I'm going to write out my electric field, which is in the radial direction in both cases. When r is less than r, of course, I'm going to have nil, 0 electric field. It looks weird to have the r out there. And when the electric field is outside the sphere, then I'm going to have non-zero electric field. It's going to be 1 over 4 pi epsilon naught q over r squared r hat. Now from this, the potential is not too bad. Because remember, what is the relationship between the electric field and the electric potential? The relationship that is permitted because the curl of the electric field is 0. Well, to get the electric potential from the electric field, we know that the electric potential is nothing more than minus the integral of the electric field. And if you're wondering just like me, oh, where does that minus sign come from? It is nothing more than a consequence of integration. When you integrate 1 over r squared, you happen to get minus 1 over r. To kill that minus sign, we have to multiply it with another minus sign, giving us a positive potential for positive charges. That's the motivation behind that minus sign. All it is a mathematical convenience so that the potential for positive charges is positive. Okay, well now we're simply going to have to integrate both of these and negate them afterwards. So let's do it. I'm going to first integrate the outside electric field for the reason that I explained earlier, because it's closer to the ground. So I'm going to have minus the integral from infinity, from my ground, all the way out there, spatial infinity, to some stopping point, r prime equals r. And my integrand is going to be 1 over 4 pi epsilon naught q over r prime squared dr prime. I'm priming it, putting a prime on it, because that is the variable I'm integrating over, a common practice in electromagnetism. So we're going to have the integral of 1 over r prime squared is going to be minus 1 over r prime. Minus times minus gives you positive, so that you have 1 over 4 pi epsilon naught q over r prime, as r prime goes from infinity to r. And so let me write this over here. I'm going to have 1 over 4 pi epsilon naught. Let's put my q upstairs. And my upper limit is 1 over r. My lower limit, infinity. 1 over infinity, of course, is nothing more than 0. And so my electric potential outside should be 1 over, or q over 4 pi epsilon naught r. So let's write that down. So this is going to be q over 4 pi epsilon naught capital R, no, just lowercase r. There you go. And of course the electric potential has no direction, hence it is just a scalar, right? There you go. That's your electric field, electric potential outside the sphere. Now let's take a look at the potential inside the sphere. Well, the integral of 0 is just going to be 0, right? It doesn't matter where you're going from. You know, whether you're going from infinity to r or from r to whatever, the potential for 0 is just going to be 0, right? But we have to set the electric potential outside to the boundary, right? That's what makes it non-zero. And the boundary is r equals capital R. So the electric potential inside, when r is less than capital R, is going to be q over 4 pi epsilon naught capital R. So there you go. There's your potential inside and your potential outside for this problem. Okay, let's take a look at part D. Find the energy stored in this arrangement. Well, we recall that the energy for any electrical arrangement is simply epsilon naught over 2 times the integral of the electric field squared over the volume. Now, in this case, we have to break up this integral. You have to be very, very careful when you find the energy stored in an electrostatic arrangement that you break up that integral, because the electric field is not necessarily the same in all regions. In fact, it often isn't. As in this case, when the electric field is 0 between r is lowercase r and capital R, and when it's non-zero when r is outside the sphere. So, moral of the story, when it comes to finding the electrical energy, please break down your electric fields. In this case, I'm going to break down my electric field from 0 to capital R and from capital R to infinity. So, for my first integral, what will I have? Well, the electric field inside is simply 0. So it doesn't matter what my differential volume element is. So let's simply proceed with my second integral from 0 to capital R. Although it is disturbing for me if I don't write down the differential volume element. So 0 to the second integral should go from capital R to infinity. My electric field outside is this, 1 over 4 pi epsilon naught q over capital R all squared. Or sorry, this is lowercase r squared. And of course, what am I going to have for my differential volume element? Well, it's a differential volume element for a sphere, right? And for a sphere, we know that dv is no more than r prime squared sine theta prime dr prime d theta prime d phi prime. So now this should be a primed coordinate. This should be r prime squared. Now I can proceed with my integration. Let's do it. So of course this is going to be multiplied by epsilon naught over 2. This integral is nothing more than 0. Let's evaluate our second integral. Our second integral, let me just write it out nicely. So first things first, let's see what parts of this integrand are not involved with the integration. Notice that 1 over 4 pi epsilon naught and capital Q are all constants. So let's pull them out. And furthermore, notice that theta, well, sine theta, sine theta, d theta prime, d phi prime, we can evaluate all of those at once. They will give us 4 pi. And so what we're going to be left with here is 4 pi over 4 pi epsilon naught squared times that q squared from earlier. And this is all going to be multiplied by the integral from r to infinity of 1 over r prime to the 4th after I square it times r prime squared dr prime. Now r prime squared over r prime to the 4th, that's just going to result in r prime squared on the denominator. And I'm going to integrate that from capital R to infinity. Now of course this 1 over r prime squared, that's nothing more than negative, right? Negative 1 over r prime. So let me write all of this here. Minus 1 over r prime evaluated from capital R to infinity. Well, let's plug in our limits, shall we? This is going to be negative 1 over infinity minus 1 over capital R. Well, 1 over infinity is simply 0, and minus 1 over capital R is simply 1 over capital R, positive. So this is going to give us the total energy for our electrostatic arrangement, which is this 4 pi and this 4 pi squared cancel out. So what are we going to be left with? Silly me, I forgot that there was a factor of epsilon naught over 2 on the outside. So my final electrostatic potential on my electrostatic energy is going to be epsilon naught over 2 times all of this mess. So this epsilon naught and this epsilon naught, one of them cancel out, that was a square, and this 2 and 4 pi makes 8 pi. So my final answer is going to be q squared over 8 pi epsilon naught capital R. There you go, folks. That is the energy of this electrostatic arrangement. Now let's take a look at part E, or rather part D. No, part E. Find the general electric potential in terms of solutions to Laplace's equation in spherical coordinates. So here comes the Laplacian in spherical coordinates. I am super excited to introduce it to you. I cannot be more excited, but I have to take it one step at a time. I will explain every single term that I put down, but I will not derive it. If you want me to derive it, leave a comment down below. I'm sure there will be a comment from future refas. But for the moment, we will not focus on the derivation, but rather the application of this formula. So for part D, or rather part E, we have to write down the general electric potential in terms of solutions to Laplace's equation in spherical coordinates. So the solution to Laplace's equation in spherical coordinates, neglecting the phi hat direction, is as follows. The integral from L equals 0, note that the starting is not 1, but rather 0, to infinity of, see how it's similar to a summation? Remember that in xyz, or let's do xy, we had a summation from, for example, m equals 1 to infinity. Of course, it's going to be a summation here in this case too, right? Because we want to take all the x's and y's we have and bunch them up together to create the desired potential, right? We're trying to create a linear combination of stuff, of the basis set, so that we can create the desired potential. Okay, so you can see we have something similar. A summation here, a summation here. Summation for rectangle, a summation for spherical. Now, spherical is going to go up way, it's going to be so weird. But let me just write it down and I'll explain it step by step. My first thing I'm going to write down is this linear term. This Isabel, you can just ignore it. It's a constant. In fact, I'm not even going to bother to write it for now. I will bother to write it soon, but right now, all you have is a linear term, r to the power of L, right? So that's that. And then we have an antilinear term, a term that is not linear, right? It's just 1 over r to the L. In fact, let me modify it a tad bit. It's 1 over r to the L plus 1. Now let me add my constants, which will help us mix and match kind of how much we want of each ingredient. Let's say I want a lot of these, but not a lot of these ingredients. I can so choose that. And now I'm going to multiply all of this by something known as the Legendre or Legendre polynomial, P sub L of cosine theta. This Legendre polynomial is defined as follows. If you see P sub 0 of cosine theta, in other words, if L is 0, then this is going to be equal to 1. If L is 1, this is going to be equal to cosine theta. If L is 2, this is going to be equal to 3 cosine squared theta minus 1 over 2, and so on and so forth. So those are the Legendre polynomials. Now, in rectangular coordinates, you had your constant, let's call it C sub n, and you had your exponential terms, and you had your sinusoidal terms. I'm just going to call them x and sine y, just for keeping things simple here. You might think, well, how in the world are they similar in any way? How can I even justify this being the electric potential for the spherical Laplacian? Well, there's a few ways you can justify it. First of all, here you notice that everything is expressed in terms of r and theta, right? No more are we in the gentle worlds of exponential x's and sinusoidals, because now the basis set for us is the radial direction and theta. Now for us we have a linear term and an antilinear term, and all of this times the Legendre polynomial, P sub L of cosine theta. But there's deeper justification yet for this. Let me show you that justification. Let's write out the terms for L equals 0 and L equals 1 for the spherical electric potential in Laplacian. So we're going to have the L equals 0 terms. What are they? Well, we're going to have a sub 0 r to the 0 plus b sub 0 over r to the 0 plus 1, all multiplied by p sub 0 of cosine theta. Likewise, let's write out the terms for L equals 1, which are going to be a sub 1 r to the 1 plus b sub 1 over r to the 1 plus 1, all times p sub 1 cosine of theta. Let's work through this step by step. R to the 0, that's nothing more than 1. R to the 0 plus 1, well, I can just write that as r to the 1 or just r. R to the 1 here is just r, and r to the 1 plus 1 is simply r squared. P sub 0, the 0th Legendre polynomial, is simply 1, so I may simply disregard it. And p sub 1 of cosine theta, the first Legendre polynomial, is simply cosine of theta. So in fact, I'm going to rewrite the second electric potential term as all of that multiplied by cosine theta. So what's going on here? What are we dealing with? Let's take a look at this. First thing you'll notice is this, a sub 0. In fact, I'm going to label these 1, 2 for this linearly decaying term, not exponentially decaying, but linearly decaying, so it's a little weaker. This linear term, a sub 1 times r, in fact, a sub 1 times r times cosine theta, so we should acknowledge that. And my final term, which I will demarcate in brown, is decaying as a square, r squared. And of course it also involves cosine theta. Let's take a look at our first term here. My first term here is what? It's just a constant. So you know how you come up with the right answer sometimes in your homework, but it's just off by a little bit, and so you nudge things a little bit and get the right answer? Well, this is your fudge factor. This A naught kind of helps you tinker things up and down. That's it. It's just a fudge factor. It's just a constant potential. Constant potential. You can think of it as just a constant V naught. What about our second term there? Now that's a little sophisticated. That second term is B naught over R. The B naught is just a constant, but that 1 over R, gee, that reminds me of something. Is that not the electric potential for a point charge? Yes, sir. That is V for a point charge. Right? Remember, a point charge has an electric field of 1 over 4 pi epsilon naught Q over R squared. The electric potential is going to be 1 over 4 pi epsilon naught Q over just R. Right? That's what you're seeing right here. What about our third term? Where could that be from? I mean, I don't recognize that as anything, do I? That third term is a sub 1 r times cosine theta. A sub 1 r times cosine theta. Well, r cosine theta, is that not just z in polar? When I go from spherical coordinates to rectangular, r cosine theta becomes z. And so this is simply what? Well, think about it carefully and you'll realize this right here, that's the electric potential for a uniform electric field that's going down in the negative direction. So this is the electric potential for an electric field that's going like this. That's uniform going down. Because when you take the integral of this minus the integral of, let's say, E sub naught dz, well, E sub naught is in the negative direction, so that's going to take out this negative, and you'll just have E sub naught times z. That's what we see. Okay, and what about our fourth term? That looks almost alien to me. What is that term? That's pretty freaky, so let's write it out. That term is b sub 1 over r squared times cosine theta. Wait a second. When I write it out like that, it almost looks familiar. Cosine theta? 1 over r squared? That's one step away from being the electric field for a dipole. Hence, this is the electric potential for a dipole. You know, you might have not noticed this because we haven't introduced dipoles yet, so I don't blame you. But a dipole is nothing more than a positive charge and a negative charge separated by some distance d. And if you know a little bit of Regents physics, you might know that the electric field for this thing is something like the dipole moment over 4 pi epsilon naught over r cubed. Not r squared, but r cubed. And this dipole moment right here is qd, where q is the charge on each of these charges. So that right there, in fact, that's qd, but what if you're dealing with a more complicated charge situation? Then it becomes more like q dot r hat, which is equal to qr. Since r is a unit vector, it just becomes q cosine theta. That's what we have right here. We have our constant times cosine theta over r squared. That is the potential, the electric potential for a dipole. Because when you integrate a 1 over r cubed field, you get a 1 over r squared potential. So this right here, ladies and gentlemen, is the potential for a dipole. Isn't that exciting? So what you're seeing right here is that this right here, you're seeing the basis set. This is the basis set. This is the basis, the fundamentals out of which all other charge distributions are created from. Right? Think about it. Think about it. I've had a revelation just explaining it to you right now. Any charge distribution you create is going to either, of course, it might involve a very boring constant field. Of course, it's going to involve point charges. You got to make your charge distribution out of something, right? Something starts from something, and that's got to be point charges. That's the fundamental unit for a charge distribution. But hey, let's say you got to get a bit creative. What if you have some kind of a constant electric field? Well, you've got the ingredient for that too. And hey, what if you have dipoles, right? What if you have dipoles or quadrupoles? Well, that's where this term comes in, right? And so what you're really seeing here is that the basis for any charge distribution is staring at you right here. You've got dipoles, you've got constant potentials, you've got constant field potentials, you've got the potential for a point charge. Everything's in here. You want to make something? Go make it. Everything is here. So the world is your oyster when you have these 4 fundamental ingredients. And of course we could go on, and we'd see the potential for a quadrupole, for an octupole. And so this is really what's in this thing. All you're seeing right here is a really nicely packaged basis set. In other words, we're giving you the colors, make a painting. Okay, so that's the idea. That's really the beauty of the spherical Laplacian. Okay, so now we have found the electric potential outside. Okay, write the general potential in terms of the solution. Hopefully I've explained it very beautifully, but please, if you have any questions at all, leave them down in the comments below and I will answer them. Because the worst thing in the world is to be confused. But the best thing in the world is to understand why you were confused and understand the solution to your confusion. So now that we have dealt with part E, right, the general electric potential in terms of solutions to Laplace's equation in spherical coordinates, let's take a look at part F. Find the electric potential inside and the electric potential outside for the sphere. All right, folks, let's start part F. Find the electric potential inside and outside for the sphere. So, what is the electric potential inside and outside the sphere? Let's check it out. So, first thing I'm going to do is think this. Hey, I know the potential inside has to be 1 over 4 pi epsilon naught q over capital R. And I know the potential outside has to be 1 over 4 pi epsilon naught q over lowercase r. And I know that from part C. So that's going to help me inform what A sub L and B sub L are going to be. So let's do it. So let's see if we really can make these potentials. Let's see if we can make it happen. Let's go. So the potential inside, right off the bat, I know something, and that is this. 1. You see these two terms here, A sub L r to the L and B sub L of r to the L plus 1? One of these terms has to die for the electric potential inside. Why is that? Well, let's think about it. I know that my ground, the electric potential at infinity, is 0. Okay, the electric potential at infinity is 0. Now, the electric potential cannot be infinity anywhere, right? I mean, if the electric potential is infinity at any point, that's like a physical wall. Things cannot be there, right? It's like a barrier. So we have to prevent things from being infinity, okay? We have to prevent the electric potential from reaching infinity, from shooting out to infinity. But wait, if I'm looking at my electric potential inside the sphere, and I'm tunneling inside, I'm gone, I'm inside, then this term is going to get smaller. But this, and eventually approach 0 as r approaches 0, but this term is going to explode. It's a 1 over r term, right? It's a 1 over r term. So it's going to explode. We cannot have any of these terms if we want the electric potential inside. Because this term, as r, the radius, gets smaller, as I'm going inside and inside, this term is going to get bigger and bigger, right? As I go inside, r gets smaller. 1 over r to the L plus 1 gets bigger. This term is going to approach infinity at the center of the sphere. So this term has to die. It has to go. So the electric potential inside must not have any B sub L terms. In other words, for the electric potential inside, B sub L equals 0 for all L. So what is our electric potential inside going to look? Well, I have no idea what my constants are going to be, but straight off the bat, I know that this term is not going to exist. It's going to be gone. I have the power to do that. Isn't that amazing? I have the power to just say, this term, it doesn't fit my boundary conditions. It doesn't match what I want from my potential. It's got to go. Right? You're almost constructing the electric potential out of thin air from these basic ingredients. It's amazing. So, V sub r comma theta, electric potential inside, is going to be the summation from L equals 0 to infinity of A sub L r to the L P sub L cosine theta. Notice how I did not write this term at all. That B sub L term is gone for good. Now let's take a look at the electric potential outside. We're not done yet. Just like the rectangular case, we have to find out our expansion coefficients, but let's still find the electric potential outside, and then we'll deal with finding our expansion coefficients. So we have V out. So the electric potential outside, well, how the tables have turned, my friend. Because observe this. When I go outside, and I know what is the little thing I cannot have, that little thing is that when I have an electric potential of infinity, that's a no-go. I cannot have an electric potential of infinity. I just can't. Because that's like creating a wall where no charges can go, no charges can enter. Right? So I don't want any barriers, no walls in my story. All I want are non-infinity electric potentials. Very strange how I said that, but indeed that is the case. So notice that as I go out, all the way to infinity, my electric potential's gotta be reaching 0, right? Okay, well, let's say R is getting bigger and bigger. Okay, well, this term is gonna just go bigger and bigger. This term is gonna get smaller and smaller as R becomes bigger and bigger. This term is just going to keep going. It's going to get big and big and big and big. It's just like the exponential we had for rectangular. This guy's got to go. It's got to be 0. for the electric potential inside. For the electric potential outside. Wow, it is so dangerous to say the wrong thing right here now, because one misconception can destroy your entire understanding of this very fragile, very difficult idea. So, since we want the potential to reach zero at spatial infinity, we cannot have this term. It is like the exponential term, the growing exponential term in the rectangular Laplacian. It's just going to keep going and going and going and gone, right? It's just going to keep growing. We don't want the electric potential to be infinity, and hence we're going to make A sub L equals 0 for all L. There's a reason I'm spending so much time explaining why these two guys have to be what they are, why B sub L has to be 0 for all L inside, and why A sub L has to be 0 for all L outside. Not only because this occurs frequently in problems involving the spherical Laplacian, but also because it's a fundamental idea, and it pops up in many different places in different forms, and you really have to get to the bottom of this idea to understand it in its many forms. Okay, so that is the key idea for why B sub L is 0 inside the sphere, and why A sub L is 0 outside the sphere for all L. So now we can say what the electric potential is going to be outside. So V sub out as a function of r and theta is going to be much the same, but now only without the A sub L term and only with the B sub L term. L plus 1 P sub L cosine of theta. Well, now all that's left is meeting my boundary conditions, which is right here. Or rather, you can look at your conditions right here, which is the potential inside has to be this. Has to be this. Well, what is that? Let's take a look. So the potential inside, let's write out our first two terms. Our L equals 0 and L equals 1 terms for the potential inside are going to be A sub 0, r to the 0, P sub 0 of cosine theta, plus A sub 1 times r to the 1 times P sub 1 of cosine theta. And perhaps we'll need more terms. All of this has to equal this, 1 over 4 pi epsilon naught Q over capital R. Well, let's see. All of that is just, wait a second. Isn't all of that a constant? Look, 1 over 4 pi is definitely a constant. 1 over 4 pi epsilon naught. Q is a constant. And this is a capital R. It's not a lowercase r that can change. This is capital R. It's fixed. I'm not going to have any cosine. P1, remember, is cosine theta. P sub 1, the first legendary polynomial, cosine theta. That's gotta be gone. This second term, we don't need that. We don't need any future terms. All we need is this stickler. The first the zeroth legendary polynomial is just 1. We don't care. It's like it doesn't exist. R to the 0 is just 1. It's like it doesn't exist. That means A sub 0, that constant has to be this. You see now, we've just made something, we've just made the potential we desire out of the most basic ingredient, the constant term. So, I mean, you might think, okay, well, who even needs that constant term? Turns out this fundamental basic problem where you have a spherical conductor, the electric potential inside involves this constant term, right? So, for the electric potential inside, we're simply going to have what we had before, which is this, only now we can write it in terms of spherical coordinates. So for the electric potential inside, we're going to have simply an A sub 0th term. That's all we're going to have. So the electric potential inside is simply going to be A sub 0, where A sub 0 is 1 over 4 pi epsilon naught capital Q over capital R. So now let's take a look at the electric potential outside. Outside, we're going to, once again, write out all the terms. Not all the terms that would take an infinitely long time. We're just going to write out the first two terms. B sub 0 over r to the 0 plus 1, which is just r, times P sub 0 cosine of theta. You know what, let me write it out because this might be the first time. Equals one term is B sub 1 over r to the 1 plus 1 P sub 1 cosine of theta. Now let's simplify this, and of course we might possibly need more terms. All of this has to equal this bad boy, 1 over 4 pi epsilon naught capital Q over lowercase r, meaning we do indeed have a variable in this case, meaning that this guy is going to change. It's going to change. R is going to move around, move about, okay? So let's take a look and simplify some stuff. P sub 0, that's just 1. P sub 1 of cosine theta, well, that's just cosine of theta. That's the first Legendre polynomial. I always love saying that man's name. R to the 0 plus 1, well, what is that but R? And R to the 1 plus 1, well, that's just R squared. Now, shall we? Is there any 1 over R squared over here? Do you observe that? Do you observe any cosine theta or higher order terms in our desired potential? No. And no means they must go. All of these must die. Because all we need is a first order inverse R term, and we don't need any cosine terms, for God's sake. So all of these guys just go. We don't need you. All we need is this B naught over R term. Well, B naught over R, let's compare that to this. Over R over R. B naught, therefore, must be all of this. Right? And so, the electric potential outside is nothing more than B naught over R. Where B naught is 1 over 4 pi epsilon naught Q. Isn't that wonderful? Isn't that wonderful? And you might even think, this is a little bit overpowered for me. I mean, why would you even use the spherical Laplacian if you could simply find the electric potential by negating the integral of the electric field over space? Well, the answer to that question, my friends, is this. The spherical Laplacian works best when you have complicated spherical problems, such as what if you have a spherical conductor inside a uniform electric field? Then as you go farther and farther away, the electric potential will approach not zero. That won't be your ground. Oh no, the electric potential is going to approach the electric potential of the constant uniform electric field. So you can concoct crazily strange potential problems where you need the Laplacian in spherical coordinates. In fact, in the future, we're going to be examining problems such as I said, a spherical conductor in a uniform electric field. And those will require, you cannot use the standard, use Gauss's law and then find the electric field and then integrate the electric field over a certain path and then negate it to find the electric potential. You can't do that because you can't use Gauss's law. Maybe there's no symmetry. Maybe you don't know the volume charge density. Maybe there's some crazy spherical things going on. Maybe that crazy spherical conductor is in a uniform electric field. All kinds of crazy things can happen. And that's where the spherical Laplacian comes to save the day. Well, ladies and gentlemen, I hope you've learned a bit from this episode, and I can't wait to see you next time.